Take a ruler, cut it in half. Cut that half in half. Keep going. After 35 cuts, you hit a wall the universe will not let you cross. This is the Planck length, a distance so small a proton looks like a galaxy beside it. Today we journey to where space dissolves into pixels, where time stops ticking, where black holes form from a single photon, and where reality itself might end. If this fascinates you, like and subscribe. It helps us reach more curious minds. Now close your eyes. We're going smaller than small. Hold a grain of sand between your fingers. Inside that grain sit trillions of atoms. Inside each atom, a nucleus. Inside that nucleus, a proton. And inside that proton, you would still need to shrink down by a factor of 100 quintillion before you reach the number we are about to discuss. That number is 1.6, followed by a decimal point, followed by 34 zeros, followed by a 1 written in meters. Scientists call it the Planck length. It is the smallest distance that has any meaning in the laws of physics we currently understand. To grasp how absurd this size is, try a comparison. If the universe was scaled down so that a quarter were the size of a Planck length, the entire observable universe would be about 1/100th the width of a human hair. Read that again. Shrink a coin until it becomes a Planck length, and the cosmos itself, with its hundreds of billions of galaxies, becomes thinner than a strand of hair on your head. This is not an exaggeration. This is the actual math. The Planck length is so small that no microscope built by humans or buildable by any civilization in any galaxy will ever resolve it. The most powerful particle accelerator ever constructed, buried under the border of France and Switzerland, peers down to about 10 to the 19th meters. The Planck length sits 16 more zeros below that. 16, each zero a factor of 10 times smaller than the last. What makes this number so haunting is not just its size. It is what happens at this scale. The familiar universe, the one made of smooth space and flowing time, simply stops working here. Atoms have a definite position. Stars sit in definite places. But at the Planck length, position itself becomes meaningless. Distance loses its grip. The very ruler you would use to measure it bends, melts, or collapses into something far stranger. Some physicists believe the Planck length is the resolution of reality. Like the pixels on a screen, every point in space might actually be a tile, and you cannot zoom in past the tile. Others argue space stays smooth all the way down, and the Planck length simply marks where our equations break apart. Both groups agree on one thing. Below this distance, our two greatest theories of nature, Einstein's general relativity and quantum mechanics, contradict each other so violently that physics itself stops giving answers. It gets stranger. To even attempt a measurement at this scale, you would need to pack so much energy into so small a volume that the volume would crush itself into a black hole before any information could escape. The act of looking destroys the thing you are looking at. The universe, in a sense, has put a fence around its smallest secret and posted a guard made of pure gravity. This is the strangest fact in modern physics. Reality may have a final, unbreakable resolution, and we are only just beginning to understand what that means. To see why, we have to go back to the man who first calculated this number, working alone at his desk in Berlin in the year 1899. He had no idea what he had just found. What he scribbled on his page would haunt physicists for the next century. Max Planck was not trying to find the smallest distance in the universe. He was trying to clean up his equations. The year was 1890. Planck, a quiet professor in Berlin, sat at his desk surrounded by papers covered in symbols, like every physicist of his time. He was annoyed by something simple. Every formula in physics depended on units, meters, seconds, kilograms. These units were chosen by humans, based on the size of the Earth, the swing of a pendulum, the mass of a lump of metal in a vault in Paris. They were arbitrary. If aliens existed and tried to compare notes with us, none of our numbers would match theirs. Planck wanted to fix this. He wanted units that any intelligent being in any galaxy would arrive at by pure logic, so he reached for the most fundamental constants in nature, the speed of light, the constant of gravity, and his own newly discovered constant, the one that governed the quantum world. He combined these three numbers in a specific way, multiplied and divided them, took a square root, and out fell a length. That length was unimaginably tiny, about 1.6 times 10 to the negative 35th meters. Planck had no clue what it meant. He simply noted that it was a natural unit, free of human bias, and moved on. For decades, almost nobody cared. The number sat in textbooks like a curiosity, a footnote. It was too small to matter. Atoms were already absurdly tiny, and this length was 100 quintillion times smaller than that. Why would anything ever happen at such a scale? Then, in the 1950s and 60s, physicists began to notice something unsettling. When they tried to merge gravity with quantum mechanics, equations exploded. Numbers ran off to infinity. Probabilities turned into nonsense. And every time the math broke, the breaking point was the same. It was a distance, a specific distance. Planck's forgotten little number. The universe, it seemed, had drawn a line. On one side, our equations worked beautifully. On the other side, they shattered, and the line sat exactly where Planck's combination of constants placed it. This was no accident. The three constants Planck used each represent a wall in nature. The speed of light is the wall of fastness. Nothing crosses it. The gravitational constant tells you how strongly mass curves space, and the quantum constant tells you how fuzzy reality becomes when you look closely. Mash these three walls together, and you get a length where all three effects matter equally, a place where light, gravity, and quantum fuzziness collide in one chaotic point. Below that point, reality stops behaving. Above it, physics breathes easy. What Planck stumbled onto by chance was the address of the universe's basement. He just did not know it. He thought he had cleaned up his units. In truth, he had handed every future physicist a map to the deepest unsolved problem in science. And the strangest part of his discovery is something almost nobody notices. The Planck length is not built from anything human. It is not measured. It is not chosen. It falls out of the constants of nature themselves, as if the universe had its own preferred ruler hidden inside its own laws. But to understand why this ruler hits a wall, we need to do something simple. We need to start cutting. Take a ruler 1.5 meters long, roughly the height of a child. Now cut it exactly in half. You have something the length of a forearm. Cut that in half, the size of a hand. Cut again, the width of your palm. Each time you halve, the piece shrinks by a factor of 2. Keep going. The thickness of a finger, the width of a pencil, the diameter of a hair, the size of a single human cell. Already you are at scales the eye cannot see, but the universe is in no rush to stop you. Cut the cell, cut the molecule, cut the atom, cut the nucleus, cut the proton, cut the quark inside the proton. You have now cut your ruler about 25 times. The piece in your imaginary hand is so small that no microscope on Earth could detect it. And yet, in mathematics, you can keep cutting forever. There is no number too small to halve. Half of any number is just another number. But the universe does not care about your math. After about 35 halvings, something extraordinary happens. The piece you are holding is exactly 1 Planck length across. You raise your scalpel for the next cut, and the universe stops you. It is not that your blade is too dull. It is not that no microscope can see well enough. It is that the act of cutting the piece in half, of even defining where the middle is, would require energies so enormous that the piece itself would collapse into a black hole. The blade vanishes. The ruler vanishes. The very idea of half loses its meaning. This is one of the most disturbing facts in physics. We have always assumed space is like a smooth highway. You can drive any distance, no matter how tiny, a millimeter, a micrometer, a picometer. The road keeps going, but the Planck length suggests the road has a final marker, a point past which there is no further pavement. Not because the road ends, but because the very concept of distance breaks down. Some physicists describe it like the resolution on a screen. Watch a movie on a phone. Zoom in more. Eventually you hit individual pixels, and zooming further only blurs them. The image cannot get sharper. Reality may behave the same way. Below the Planck length, the concept of a point-like particle or infinitesimally small distances might lose its physical meaning at this scale. Now imagine what this means for everything else. Your hand is not made of an infinite number of points. It is made of a finite, almost unimaginably large, but limited number of Planck scale tiles. The chair you sit on, the earth beneath your feet, the sun in the sky. Every object in existence, when zoomed all the way in, runs out of room to be cut. Reality in this picture is not a continuous painting. It is a mosaic. And every mosaic has a smallest tile. Whether this is literally true or just a sign that our equations are incomplete remains an open question. But the wall is real, 35 cuts. And then nothing. To understand why this wall sits exactly where it does, we have to compare its size to something familiar. And the familiar thing we will pick is the proton. A proton is small, almost insultingly small. If you took a single proton and inflated it to the size of a basketball, then a basketball at that same magnification would become larger than the entire Earth. The proton sits at about 1/10 trillionth of a centimeter across. Already this is a number so absurd that the human mind has no real way to picture it. We just nod and say, very small. Now here is the punch. The Planck length is about 10 to the negative 20th times the size of a proton. Stop for a moment and let that sink into your bones. A proton is to you roughly what you are to the entire solar system. And the Planck length is to a proton what a proton is to a city the size of New York. To go from a proton down to a Planck length, you have to shrink by 20 more zeros. 20. Try this comparison. Imagine the proton blown up to the size of our solar system, with the orbit of Neptune as its outer edge. In that imaginary system, where the proton fills the space between the Sun and the outer planets, the Planck length would still be smaller than a single grain of sand sitting on a beach in California. The smallness keeps stacking. It does not stop. It does not slow down. Every level of zoom reveals more emptiness, and the Planck length still waits at the bottom, almost mocking the very idea of small. This raises a question that every honest physicist must face. Why does the universe care about a length so far below anything we can ever touch? Atoms work fine without ever knowing the Planck length exists. Stars burn for billions of years without consulting it. Galaxies spin, planets orbit, life evolves, all at scales unimaginably larger. And yet, the math says the Planck length is the place where the foundations of reality are laid. Like the steel beams holding up a skyscraper, you never see them, you never touch them, but if they fail, the entire building falls. The Planck length is the steel beam beneath the cosmos. Here is the unsettling part. Our most powerful machine for probing tiny distances is the Large Hadron Collider in Switzerland. It accelerates protons to ridiculous speeds and slams them together, peering into the wreckage. Its current resolution reaches about 10 to the negative 19th meters. Compare that to the Planck length at 10 to the negative 35th meters. The collider is 16 orders of magnitude away, 16, each one a factor of 10. To reach the Planck length, we would need a machine not 10 times more powerful, but 10,000 trillion times more powerful. A device the size of a galaxy, or possibly larger. This is why the Planck length feels like a horizon, not a wall we are walking toward. A horizon we will never reach by walking. And yet the universe operates at this scale every nanosecond of every day. Every photon, every particle, every empty pocket of space, all of it ultimately rests on a structure we will never see directly. But there is one thing about light itself that may have already brushed against this limit. Light travels in waves. You already know this. The waves you see with your eyes, the visible kind, have wavelengths roughly 0.5 of a meter. Red light is shorter. Below violet, we get ultraviolet, then X-rays, then gamma rays. Each step, the wavelength shrinks. Each step, the energy of the wave climbs. Gamma rays have wavelengths smaller than an atom. They carry so much energy that one of them, hitting your DNA, can rip a molecule apart. This is why we shield ourselves from radiation. The shorter the wave, the more dangerous the punch. Now imagine pushing this further. Compress the wave more, squeeze it tighter, make the wavelength smaller than a nucleus, smaller than anything we have ever measured. The energy keeps climbing, doubling, tripling, multiplying without limit. There is a problem. Energy and gravity are linked. Einstein showed us that energy bends space the same way mass does. So as your wave packs more and more energy into a tinier and tinier volume, it also bends the space around it more and more violently. Eventually, you reach the Planck length. And here, something unforgivable happens. Even if we could create a photon with a wavelength shorter than Planck, it would carry so much energy in such a small area that it would collapse into a black hole before it could return any useful information. Read that twice. The light itself becomes a black hole. Picture the moment. You are firing a photon, the messenger of light, at a target. Its wavelength is your magnifying glass. The shorter the wave, the sharper the picture. You crank the energy higher, trying to see more. The wavelength shrinks. The picture sharpens. Then, just as you approach the Planck scale, the photon crosses an invisible threshold. Its energy, packed into a Planck-sized volume, exceeds the limit of what space can contain. Gravity wins. The photon folds in on itself. Light becomes darkness. This is not a thought experiment. This is what the equations say happens. The implications are staggering. Light, which we used to think of as the most pure and weightless thing in the universe, has a hard floor it cannot go beneath. There is no such thing as a wave shorter than a Planck length. Not because we cannot make one, because the universe will not allow it. Try to make one, and gravity erases it. This means the Planck length is not just a wall for human technology. It is a wall for light itself. The fastest, most fundamental messenger in nature has a smallest possible step. And that step, once again, is the same number Max Planck scribbled on his desk over a century ago. There is something almost mythological about this. Light is the tool we use to see, and yet light has its own blindness. There is a region of reality where light can never go, because the moment it tries, it eats itself. Some physicists wonder if this is why the universe looks smooth at every scale we can probe. Maybe the Planck-level chaos is hidden from us not because it is too far away, but because the very thing we use to look, light, breaks before it gets there. The fence around the basement of reality is built from gravity itself, and the next chapter shows just how unforgiving that fence is. The universe has a security system. Try to peek too closely at its smallest scale, and the system fights back. It does not just block your view, it manufactures a black hole on the spot, swallows the data, and leaves you with nothing. This sounds like science fiction. It is not. It is a direct consequence of two of the most well-tested ideas in all of physics. The first idea comes from quantum mechanics. To see something tiny, you need a probe with a wavelength smaller than the thing you want to see. Want to see a virus, you need wavelengths shorter than a virus. Want to see an atom, you need wavelengths shorter than an atom. The smaller the target, the shorter the wave, the higher the energy of your probe. The second idea comes from general relativity. Squeeze enough energy into a small enough volume, and that volume collapses into a black hole. There is a specific size, called the Schwarzschild radius. Where this collapse becomes inevitable, pack a star into the size of a city, you get a black hole. Pack the Earth into the size of a marble, you get a black hole. Now, combine these two ideas. To see something Planck-sized, you need a probe with Planck-level energy concentrated in a Planck-sized volume. But that exact concentration of energy is also the recipe for a black hole at that exact size. The math is brutally elegant. The wavelength you need for the measurement is the same length at which your probe collapses into a singularity. Push a little harder for a sharper look, and instead of a sharper look, you get an event horizon. The light goes in, nothing comes out. Your detector reads empty. The information is locked behind a wall you cannot cross. Imagine a detective trying to read a secret message written on a tiny scrap of paper. The detective uses a magnifying glass. The glass is not strong enough. He grabs a microscope. Better, but still not enough. He grabs the most powerful electron microscope on Earth. The message is still too small, so he invents a particle accelerator the size of a continent. The accelerator fires beams at the paper. The instant the beam hits with enough energy to read the message, the paper, the beam, and the surrounding room collapse into a black hole. The message is preserved, sort of, but only inside a region from which no information can escape. The detective gets nothing. This is the Planck trap, and it is not avoidable by being clever. It is built into the fabric of physics. Quantum mechanics demands more energy for smaller views. General relativity demands black holes for higher energy in tiny spaces. The two demands lock together at exactly the Planck length and slam the door shut. Some physicists call this the cosmic censorship of the small. The universe seems to refuse to let anyone, ever, look directly at its tiniest workings. Every method we devise to peek closer ends with the same outcome. The peeker creates the very object that hides what is being peeked at. This has a consequence almost no one talks about. It means the Planck length might not just be the smallest length we can measure today with our current tools. It might be the smallest length anything ever in any possible future can measure, not just for humans, for any conceivable civilization, for any imaginable intelligence, forever. The wall is not technological, the wall is woven into reality. But there is something even stranger about this wall. It connects to a principle that has haunted physicists since the 1920s, a principle that puts a price tag on every measurement. In the 1920s, a young German physicist named Werner Heisenberg discovered something that nobody wanted to be true. He proved that the universe charges a tax every time you try to measure it. The tax is simple. The more precisely you know where something is, the less precisely you can know how fast it is moving. And the reverse. Pin down the speed perfectly, and the position becomes a blur. There is no escape from this trade. It is not a limit of our instruments. It is a feature of reality itself. This is called the uncertainty principle, and it is the reason the Planck length acts the way it does. To understand why, picture a moving target. A fly buzzing in the dark. To see it, you shine a flashlight on it. The flashlight uses light, and light, as we just learned, comes in waves with energy. When the light bounces off the fly, the impact gives the fly a tiny push. You learn where the fly was, but your measurement shoved it sideways. For a normal-sized object, this push is negligible. A fly weighs millions of times more than a photon. The light cannot move it. But for a single electron, or worse, a region of space the size of a Planck length, the push is everything. To see the position with high precision, you need a high-energy probe. The probe pushes hard. The thing you measured is now somewhere else, moving at some unknown speed, energized by your measurement. This sets up a vicious cycle at small scales. You want to know exactly where a piece of space is. You fire a probe with enormous energy, because precise position requires short wavelengths, which require high energies. The energy bends space. The bent space distorts the very location you were trying to pin down. By the time you reach the Planck scale, The energy needed to specify a location is so vast that the location itself melts. The space wobbles, quantum fluctuations boil up out of the vacuum, particles wink in and out of existence, the smooth backdrop of reality dissolves into foam. This is why physicists believe space at the Planck scale is not a calm, empty stage. It is a churning, frothing, bubbling sea. Pairs of particles appear out of nothing, exist for less than a Planck unit of time, and vanish back into nothing. Tiny temporary black holes flicker and evaporate. Geometry itself stops being a fixed thing and becomes a quantum probability cloud. Heisenberg's principle, written in 1927, did not mention black holes or Planck lengths, but when extended to its logical extreme, it leads straight to them. The principle says that to know a position perfectly, you would need infinite energy. Infinite energy in a tiny region is a black hole the size of the universe. You cannot have it. So perfect knowledge of position is forbidden. The Planck length is the practical version of this rule. It is the distance at which the energy required to know a position is exactly enough to make the region collapse. Beyond it, the very concept of position stops being useful. Asking where something is at sub-Planck precision is like asking what color a song is. The question has no answer because the categories no longer apply. This is the strangest gift of quantum mechanics. It tells us that reality has a built-in fuzziness, and the size of that fuzziness has a name, the Planck length. But there is a deeper twist. To even attempt this measurement, you would need to gather a particular amount of mass into a single point, and the universe has a name for that mass too. There is a number in physics called the Planck mass. Most people have never heard of it. Compared to the Planck length, it gets almost no attention, but it may be the strangest of all the Planck quantities. How big is a Planck mass? About 22 micrograms, roughly the weight of a grain of sand, maybe a flea egg. This sounds tiny. It is tiny by the standards of everyday objects, but you have to compare it to what physics usually deals with. The mass of an electron is so small, it takes 10,000 trillion of them to add up to a single gram. The mass of a proton is 2,000 times bigger than an electron, but still nearly nothing. A Planck mass is roughly 10 million trillion times the mass of a proton. Now hold that thought, because here is the bargain the universe demands. To observe something at the Planck length, you need to focus all that mass energy into a region the size of a Planck length. A flea egg's worth of mass crushed into a volume so small that a proton looks galactic next to it. The result is automatic. You have just created a tiny black hole. This is no accident. The Planck length and the Planck mass are designed by nature to fit each other exactly. The Planck mass is precisely the amount of mass energy that, when squeezed into a Planck length volume, becomes a black hole. The two numbers are locked together by the same constants that define them in the first place. Nature has a self-consistent rule. To see her smallest features, you must conjure her tiniest possible black hole. This is why physicists sometimes call the Planck mass the threshold of quantum gravity. Above this mass, gravity dominates. Below it, quantum effects rule. Right at the Planck mass, both forces shout at the same volume, and the equations of physics tear themselves apart, trying to handle both at once. It also leads to one of the most haunting predictions in modern theory. The Planck length may be approximately the size of the smallest black holes. Read that carefully. The smallest black holes, not the biggest, not the famous ones at the centers of galaxies, the tiniest black holes that can possibly exist, according to our equations, are roughly the size of a Planck length and weigh roughly a Planck mass, microscopic, fleeting, almost paradoxically light by black hole standards. If they exist, they would form spontaneously from pure energy fluctuations in the vacuum. They would evaporate almost instantly through a process called Hawking radiation. They might have peppered the early universe in unimaginable numbers, then vanished, leaving only ghostly fingerprints in the cosmic microwave background. Some physicists have wondered if these mini black holes could be created in particle accelerators. Others have asked whether they might be hiding inside cosmic rays. So far, none have been detected, but the equations insist they should exist, at least in principle, sitting at the very floor of what black holes can be. This is the deal nature offers. To peak at the smallest distance, you need the smallest black hole. To make the smallest black hole, you need a Planck mass. And the moment you assemble that mass in the right place, the universe seals it off behind an event horizon and walks away. The bargain is one-sided. The universe gets to keep its secrets. We get to ponder. But the trouble runs even deeper than measurement. At the Planck scale, the two greatest theories ever invented by human minds turn on each other and start fighting. There are two cathedrals in modern physics. One is general relativity, built by Albert Einstein in 1915. The other is quantum mechanics, built by a small army of physicists in the 1920s. Each cathedral, taken alone, is one of the most successful theories ever invented. Each predicts experimental results to absurd accuracy. Each has survived 100 years of attacks by skeptics. There is just one problem. The two cathedrals were built on incompatible foundations, and at the Planck length, both foundations crack at once. General relativity describes gravity as the curvature of space and time. A massive object, like the Sun, dents the fabric of space, and other objects roll into the dent. That dent is what we feel as gravity. The theory works beautifully for planets, stars, galaxies, and even the universe as a whole. It predicted black holes before anyone believed in them. It predicted gravitational waves a century before we detected them. Quantum mechanics, on the other hand, describes the world of the very small: electrons, photons, atoms. In this theory, particles do not have definite positions or speeds. They live as clouds of probability. They can be in two places at once. They can leap across barriers without crossing the space in between. The theory predicts the colors of fireworks, the chemistry of life, the inner workings of every transistor in every phone on Earth. Both theories are correct, and both theories say the other is wrong about something fundamental. General relativity says space and time are smooth, continuous, a gentle curving fabric. Quantum mechanics says nothing in nature is smooth. Everything jitters, fluctuates, exists in superpositions. When you try to apply quantum rules to space itself, the smooth fabric of relativity breaks into a foam of jagged probabilities. For most of the universe, this conflict does not matter. Gravity is so weak compared to the other forces that quantum effects on space are negligible. A falling apple does not care about quantum fluctuations of the ground. The Earth orbits the Sun the same way whether or not space is fundamentally fuzzy. But at the Planck length, gravity becomes as strong as the other forces. The fuzz of quantum mechanics has nowhere left to hide. Every time a physicist tries to write equations that combine both theories at the Planck scale, the equations vomit infinities. Probabilities exceed 100%. Energies become unlimited. The math goes mad. This is why the Planck length is sometimes called the place where physics commits suicide. Imagine two perfectly tuned orchestras playing different songs in the same room. From far away, each orchestra sounds beautiful. Walk closer to either one and you can ignore the other, but stand exactly between them and the two songs collide into noise. Neither melody survives, only chaos. The Planck length is that exact spot between the orchestras, a region where the music of relativity and the music of quantum mechanics drown each other out. To make sense of what happens here, physicists need a third theory, a grand symphony that contains both songs as parts of itself. This new theory is called quantum gravity. It does not exist yet, not really. There are candidates: string theory, loop quantum gravity, causal sets. Each makes its own guesses about what reality looks like at the Planck scale. None has been proven. None has been experimentally tested at the relevant distance. All of them remain mathematical poetry. beautiful but unconfirmed. The Planck length is the riddle that humbles every physicist on Earth. It is where our smartest theories admit they do not know. And it is also where one wild idea begins to seem almost reasonable. Maybe reality has pixels. Look at a photograph on your phone. Zoom in again. Eventually, the image dissolves into squares. Each square is a pixel, the smallest unit the screen can display. There is no way to zoom past it. The pixel is the flaw of resolution. Now consider a wild but persistent idea in modern physics. What if the universe is the same? What if space is not infinitely smooth, but instead made of tiles, each one a Planck length across? What if every chair, every star, every photon, every breath you take is a pattern stamped on a grid we can never see directly? This idea has been floating around for almost a century. Werner Heisenberg himself flirted with it in the early days of quantum mechanics. The intuition is simple. Heisenberg deduced that space and time were pixelated into indivisible three-dimensional Planck length units, similar to the two-dimensional pixels on your computer screen. The alternative is that space stays smooth all the way down forever. But that picture has its own monsters. If space is truly smooth, then between any 2 points, there are infinitely many other points. Infinite in the strict mathematical sense. To move from your front door to your kitchen, you must pass through an uncountable wilderness of points. This raises ancient paradoxes that the Greek philosopher Zeno first noticed 2,500 years ago. How do you ever cross an infinite number of halfway marks? The pixel idea sidesteps these paradoxes. If space comes in smallest tiles, motion is not the smooth gliding of a finger across glass. It is more like a chess piece jumping from square to square. The squares are too small for human eyes to see, but they exist. Movement is a sequence of finite hops on a fixed lattice. If true, this would be the most radical revision of our worldview, since Copernicus put the sun at the center. It would also explain why the Planck length acts like a hard flaw. Of course, the universe stops dividing at the Planck length. It runs out of pixels. There is even a beautiful consequence. If reality has a smallest unit, then there must also be a smallest amount of information you can store in a region of space. Each pixel could carry one bit, one yes or one no. The cosmos becomes, in essence, a vast computation, with the Planck length playing the role of a single transistor. Some physicists love this idea. It connects gravity, information, and quantum theory in one tidy package. Others hate it. They point out that pixels in 3 dimensions would seem to violate one of Einstein's most sacred rules. If the grid sits still, then a moving observer should see the pixels squashed in the direction of motion. The pixels themselves should change size depending on who is looking. That breaks the symmetry that all of relativity is built on. So the pixel idea has critics, lots of them. Lorentz symmetry explains why the naive Planck pixel idea does not fit with current physics. Yet the idea refuses to die. Newer versions, like loop quantum gravity, have found clever ways to keep the spirit of pixels while patching the relativity problem. They suggest that the pixels are not fixed in any one frame, but emerge from quantum measurements made by observers, a subtle distinction, but possibly the key to making the whole picture work. Whether reality is truly pixelated or only behaves that way at the smallest scales, one thing is certain. Something in the structure of space must give way at the Planck length. And one of the leading theories about how it gives way involves loops. In the late 1980s, a small group of physicists began chasing an idea that sounded almost too strange to take seriously. They proposed that space, instead of being smooth or even pixelated in the simple sense, was woven from tiny loops. Not loops of string, loops of pure geometry. Threads of nothing, knotted and tangled, whose pattern gives rise to what we feel as the fabric of reality. This idea is called loop quantum gravity. The picture works like this. Imagine zooming into empty space. Empty, by everyday standards, means containing no atoms, no light, no air. Truly nothing. According to loop quantum gravity, that emptiness is actually a dense network of mathematical loops, each one roughly the size of a Planck length. These loops cross, link, and braid into a structure called a spin network. The spin network is to space what threads are to a fabric. Look at a shirt from far away, and it looks smooth. Look at it through a microscope, and you see the woven threads. Look closer still, and you see fibers. The smoothness was an illusion of distance. Loop quantum gravity says space is the same. The smooth, flat universe of Einstein is what you get when you stand far away from the spin network. Up close, it dissolves into a tangle. Now here is the punch. In loop quantum gravity, area and volume operators have discrete spectra. Surfaces and volumes come in quantized units. Those quanta are of order the Planck area and volume. That is a stunning claim. It says that a surface like the page of a book or the skin of an apple cannot have just any size. Its area has to come in chunks. There is a smallest possible area. Below it, you cannot have a surface at all. The same goes for volume. You cannot have a region of space whose volume is anything you like. The volume must add up from smallest possible units, Planck-sized blocks. This is different from the simple pixel idea. The loops are not fixed in any background grid. They float, dance, and reorganize themselves. They are the grid. There is no stage beneath them. The stage is built from the loops themselves. If this is true, the universe is much stranger than common sense suggests. Empty space has structure. The structure has minimum sizes. Geometry, the queen of mathematical disciplines, is itself quantum mechanical. You cannot ask, what is the area of this Planck-sized patch, and expect a smooth answer. You get one of a discrete list of possible answers, like rungs on a ladder. This solves several puzzles at once. The infinities that destroy ordinary quantum gravity vanish, because you can never sum over arbitrarily small distances. There simply are no arbitrarily small distances. The smallest hop is the smallest hop. The math behaves. It also gives black holes a strange new property. Their event horizons in this picture are stitched together from a finite number of Planck-sized patches. Count the patches, and you can count the entropy of the black hole. Loop quantum gravity reproduces, almost exactly, a famous formula for black hole entropy, first guessed by Stephen Hawking, but now derived from first principles. There is no experimental proof yet. The Planck scale is far below anything we can probe, but the theory makes one striking prediction. Light traveling across vast distances should occasionally show small effects from the underlying loops. Photons of different colors, racing across billions of light years, might arrive at slightly different times if they pass through enough Planck scale fluff. We will return to that test later. For now, hold this picture in your mind. Reality is not a stage with actors on it. Reality is a tangle of self-organizing threads, each one the size of the Planck length, and the play we call physics is just the pattern they make as they wiggle. But loops are not the only candidate. There is another theory, older and even more famous, that also lives at this scale, and it is built from something that vibrates. String theory was born in the late 1960s, almost by accident. Physicists were trying to understand the strong nuclear force, the glue that holds atomic nuclei together. Some equations they wrote down had a weird feature. They behaved as if the particles being studied were not points, but tiny vibrating strings. At first, this seemed like a curiosity. Particles, after all, are described in textbooks as zero-dimensional points. They have a position. They have no size. Treating them as little strings felt like a step backward. Then someone noticed something. If you assumed the strings were real, and you assumed they were ridiculously small, the equations also accidentally described gravity. Not just any gravity, quantum gravity. The very thing nobody else could write down without producing infinities. The strings, the math demanded, would have to be roughly the size of the Planck length. Anything larger, and they would have shown up in experiments long ago. Anything smaller, and the equations break. This was the moment string theory stopped being a curiosity and started becoming the most ambitious idea in physics. The picture is this. Imagine a violin string. Pluck it, and it vibrates in different patterns. Each pattern produces a different note. A short string vibrating fast gives a high note. A long string vibrating slow gives a low note. The same string with different vibrations becomes different sounds. Now shrink the string until it is a Planck length long. Put it in empty space. It still vibrates. Each vibration pattern becomes a particle. One mode of vibration might appear to us as an electron. Another mode might be a photon. A third mode is a quark. A fourth mode is the elusive graviton, the particle that carries the force of gravity. Every kind of matter and every kind of force in this picture is the same thing, a string. The differences between an electron and a photon are like the differences between two notes on a guitar. Same string, different vibrations. This is why string theorists talk about the universe as a symphony. Every particle is a note. The laws of physics are the harmonies between notes. The Planck length is the size of every instrument in the orchestra. To make the math work, string theory needs more than 3 dimensions of space. It needs 10. The extra 6 dimensions are curled up so tightly that no experiment has ever felt them. Their size, you guessed it, is roughly the Planck length. They sit at every point in space, microscopic loops of geometry, like the tiniest possible coiled phone cords. This sounds outrageous. It is outrageous, but the math is breathtaking. It produces gravity automatically. It eliminates the infinities that destroy other approaches. It connects to deep ideas in pure mathematics that have surprised even mathematicians. The Caltech physicist Hiroshi Uguri once put it simply when describing why strings tame the math. The strings help soften this high-energy behavior. The energy gets spread out in a string. A point particle hit with high energy concentrates everything into zero volume. A string spreads the energy out along its length. The smearing, however tiny, prevents the dreaded collapse. The Planck-sized smear is enough to keep gravity sane. Critics point out that we have no direct evidence of strings. Decades of work, no detection. The theory has so many possible solutions that it can predict almost anything, which means it predicts almost nothing. Defenders counter that this is unfair. The Planck length is unreachable. Of course, we cannot see strings. We are 16 orders of magnitude away from where they live. To dismiss the theory for that reason is to demand the impossible. Either way, both string theory and loop quantum gravity agree on one humble fact. Whatever lives at the Planck scale is not built from the smooth nothingness of classical physics. It is structured. It is informational, and the next chapter shows just how informational. In the 1960s, a strange suspicion began to spread among physicists studying black holes. The suspicion was that black holes are not just gravitational sinks, they are also memory storage devices, and the amount they can remember is fixed by their surface area. Stephen Hawking and Jacob Bekenstein worked out the math in the 1970s. The result was startling. The information content of a black hole, measured in bits, equals 1/4 of its surface area, measured in Planck units. Translate that into plain words. Take the surface of a black hole, tile it in squares, each one a Planck length on a side. Count the tiles. Divide by 4. That is the number of bits the black hole can store. This was the first hint that information has a smallest possible unit, and the unit is set by the Planck length. Each tiny tile, roughly a Planck area in size, holds a single bit, a yes or a no, a 1 or a 0. The universe, at its lowest level, may speak in a binary language written on a Planck grid. The implications are dizzying. If this is true, then the entire visible universe contains only a finite amount of information, a staggering number of bits. Yes, but finite. Every star, every galaxy, every memory in every brain on Earth, every photo ever taken, every thought ever had. All of it ultimately reduces to a pattern of yes or no answers, stored on Planck scale tiles. The cosmos is the world's largest hard drive, and the Planck length is the size of one cell on that drive. This idea is called the holographic principle. We will meet it more deeply in 2 chapters, but first, the simpler version. Even without invoking holograms, the Bekenstein-Hawking calculation suggests that information in nature is granular. There is no smaller unit than 1 bit per Planck area. Try to pack more, and you fail. The space refuses to hold it. The data overflows into a black hole. This is not a software problem. It is a physical limit. It also flips a comforting assumption. Most people picture information as something abstract, riding on top of physical things, words on paper, voltages on a chip, patterns of ink. But the holographic picture says information is the more fundamental thing. The paper, the chip, and the ink are merely arrangements of bits written into the geometry of space itself. Some thinkers have taken this further. The American physicist John Wheeler, who coined the term black hole, spent the last decades of his life arguing that information is the foundation of reality. He summarized his belief with 3 syllables: it from bit. Every it, meaning every object, every particle, every star, ultimately comes from bit, meaning a yes or no choice in the underlying fabric of reality. If Wheeler was right, then the Planck length is not just a wall in measurement, it is the size of a single character in the universe's source code. Other physicists have pointed out a strange consequence. If information is bounded by area at the Planck scale, then the universe is in some real sense a computer, a self-running computer. The physical laws are the program. The Planck scale tiles are the memory. Time itself is the clock cycle. We are all watching and participating in the output of a vast quantum computation whose smallest operation is 1 flip on 1 Planck-sized pixel. This is no wild speculation. It is a natural consequence of combining quantum theory, gravity, and thermodynamics. The Planck length, which began as a curiosity in Max Planck's notes, has slowly grown into the address of every byte in the universe. But once you accept that reality is built from bits, you have to ask the next question. Whose bits are they? Who or what wrote the code? John Archibald Wheeler was already a legend when he started saying strange things. He had worked with Einstein. He had named the black hole. He had trained generations of brilliant physicists, including Richard Feynman. By the 1980s, Wheeler was an old man. He had earned the right to say strange things. And the strangest thing he ever said was 3 syllables long. It from bit. The it of physics, every object, every particle, every star, every brain, every thought, derives from a bit, meaning a yes or no answer to a fundamental question. Reality, at its bottom, is not made of stuff. It is made of information, of choices, of binary distinctions, of decisions about whether something is or is not. This sounds mystical. Wheeler did not mean it that way. He meant it as a serious scientific proposal. He had spent a lifetime watching physics shift from talking about objects to talking about measurements. Quantum mechanics had already taught us that particles do not have definite properties until they are measured. The act of measurement seemed to summon the property into existence. Wheeler proposed that this was no accident. The universe, he believed, was built out of measurements all the way down. And measurements, in their purest form, are bits, yes or no, 1 or 0. Was the particle here or not, spin up or down, detected or not detected? Every act of asking nature a question receives a single binary answer. Stack billions of these answers and you get an electron. Stack trillions and you get a galaxy. The Planck length enters here as the smallest place where a question can be asked. You cannot ask, what is the property of this region of space, if the region is smaller than a Planck length, because there is no well-defined region. You also cannot ask, is there a particle here, if here cannot be specified more precisely than a Planck length. The questions themselves break down. So the Planck length is the size of the smallest possible question, and the answer to each smallest possible question is a single bit. This perspective ties together every weird idea we have explored so far. The pixel theory of space, the discrete areas of loop quantum gravity, the holographic information limit on black holes. They are all whispering the same thing. The universe, viewed at its smallest scale, looks like a vast network of yes or no questions, each one taking up a Planck-sized slot, each one carrying a single bit of meaning. Some physicists have run with this idea to surprising places. Seth Lloyd, an MIT professor, has calculated the total number of operations the observable universe could have performed since the Big Bang. The answer is roughly 10 to the 120th power. A staggering number, but finite. A computer of that capacity could in principle simulate everything that has ever happened in our cosmos. Every weather pattern, every conversation, every birth, every death, every love letter, every war. All of it encoded in bits, processed through Planck-sized gates. If you find this disturbing, you are not alone. The picture suggests the universe is not a thing that exists. It is a thing that computes, and the size of the smallest gate in the smallest circuit is the Planck length. This is one reason simulation theories have gained popularity in recent decades. We will return to that question much later. For now, the more pressing point is that information theory has one more shock to deliver. The shock involves where exactly the bits are stored, and the answer is going to make your sense of reality wobble. The bits are not where you think they are. Here is a thought to break your brain. Everything you see around you, every dimension, every depth, every solid object, may be an illusion. Not in a fuzzy spiritual sense, in a precise mathematical physics paper sense. The real action, according to a startling idea called the holographic principle, takes place on a flat surface far away. What you experience as a three-dimensional world is in some deep way a hologram projected from that surface, and the resolution of the projection is set by the Planck length. The principle was born from the study of black holes. We saw 2 chapters ago that the information stored inside a black hole is proportional to its surface area, not its volume. This was deeply weird. In ordinary life, a bigger room can hold more stuff than a smaller one. The amount you can fit grows with volume, but a black hole's information capacity grows with area. Double the volume, and you can hold a little more than double. Double the surface, and you exactly double the information. It was as if the inside of the black hole did not really exist, as if the inside was just an echo of what was written on the surface. In the 1990s, physicists Gerard 't Hooft and Leonard Susskind made the leap. They proposed that this is not a quirk of black holes, it applies to everything. Every region of space, including the room you are in right now, has an information content limited by its boundary, not its interior. The interior is, in a deep sense, redundant. All the genuine information is encoded on a flat surface around the region, and that surface is divided into Planck-sized cells, each holding a single bit. The three-dimensional world, in this view, is not the fundamental level of reality. It is the way our brains decode information painted on a two-dimensional screen far away. Imagine watching a movie. The screen is flat. The people on screen seem to have depth. Their motions feel three-dimensional, but the screen itself is two-dimensional, with each frame made of pixels. The depth is a trick of the human visual system. Now imagine the same trick, but performed by the universe instead of by Hollywood. Reality, hologram style, may work the same way. The Planck-sized cells on the boundary play the role of pixels. Each one is a Planck area. Each one holds a single bit. Together, they encode the entire three-dimensional pageant of stars, planets, atoms, and minds. This idea was tested mathematically in the late 1990s by an Argentine physicist named Juan Maldacena. He found a specific case where it works exactly. A particular kind of universe in 3 dimensions can be perfectly described by a particular kind of physics on its two-dimensional boundary. The two descriptions are not just similar, they are identical. The bulk and the boundary contain exactly the same information. This was, and remains, one of the most surprising discoveries in theoretical physics. It does not yet apply to our actual universe with full rigor, but the analogy is so tight and the math so elegant that most physicists now suspect something like it is true. Our world, in some sense yet to be made fully precise, may be a hologram on a Planck-tiled boundary. If that is correct, then your sense of solidity is generated by a vast informational tapestry whose threads are Planck-sized. Reality is wallpaper, and the wallpaper is written in bits. This idea has consequences that ripple back to black holes. Because if information lives on the boundary, then a black hole is not a hole into nothing. It is a region whose information has been smeared across a surface. And that surface we have seen has a memory. The surface remembers everything that fell in, and the key to that memory is also Planck-sized. For most of the 20th century, black holes seemed simple. A black hole was a region where gravity had become so strong that nothing, not even light, could escape. Anything that fell in was lost forever. The black hole had three numbers: its mass, its charge, and its spin. Nothing else mattered. Whatever fell in was crushed into a single point at the center, and all its particular features vanished. Physicists called this the no-hair theorem. Black holes were bald. This created a paradox. Information in physics is supposed to be conserved. Burn a book, and the information is, in principle, recoverable from the smoke and ash. Smash an atom, and the information is, in principle, recoverable from the debris. But drop a book into a black hole, and the information seemed to vanish. No three numbers, mass, charge, and spin, could possibly contain the words on the pages. For decades, this was called the information paradox, and it bothered physicists deeply. Then came Bekenstein and Hawking with their stunning result. The black hole did remember. The memory was written on its surface, and the surface, when measured in Planck units, contained exactly the right number of bits to record everything that had ever fallen in. Let that sink in slowly. A black hole is not a point of erasure, it is a recording device. Every photon, every atom, every dropped book, every star that spiraled in over millions of years, all of it left a trace. The trace is written on the event horizon. Each Planck-sized patch of horizon stores a quarter of 1 bit. Sum the patches across the entire horizon, and you get the total memory of the black hole. This is why a black hole's memory grows with surface area, not volume. The information is not stored throughout the interior, it is stored on the skin. A black hole the size of the Sun has an event horizon a few miles across. Tile that horizon with Planck squares, and you get a number of bits so large it dwarfs every hard drive ever built on Earth. A black hole the size of the one at the center of our galaxy stores a number of bits that exceeds the total number of atoms in every human body that has ever existed. These numbers come from a single simple rule. The Planck length is the smallest unit of writing in nature. This insight rescued the information paradox partially. It said that information falling into a black hole was not destroyed, it was being shoveled onto the surface, one Planck patch at a time. Hawking later showed that black holes slowly evaporate, leaking energy into space as faint radiation. If information is conserved, that radiation must somehow carry the original information back out. The exact mechanism is still debated, but the rough picture is now widely accepted. Black holes are the universe's most efficient archives, and the Planck length is the size of a single character in the archive. There is a strange beauty to this. The most violent objects in nature, the ones that crush stars and warp light, turn out to be cosmic libraries. They write down everything that touches them. They burn nothing. They simply file in Planck-sized pixels on a flat horizon and let the years pass. It also makes a frightening prediction. Black holes are not eternal. They evaporate slowly, over time spans far longer than the current age of the universe. As they shrink, Their information must be released. The smallest black holes, ones with masses near the Planck mass, would explode in a final burst when they reached the size of a Planck length. Whether such tiny terminal black holes have ever existed in the wild remains an open question, but their final flash, if seen, would be a direct postcard from the Planck scale. We have not seen one yet, but we are looking. And what we may find next is even stranger than a tiny exploding black hole. Beneath the smooth surface of every region of empty space, there may be a churning storm of geometry no microscope will ever capture. When you stare at empty space, you see nothing. A blank canvas, no features, no texture, cold, dark, eternal stillness. This picture is wrong. According to quantum mechanics, the vacuum is not empty. It boils, it seethes, it hums with energy fluctuations that no instrument can fully damp. Particles wink in and out of existence. Pairs of opposite charges flash into being, exist for a fraction of a second, and annihilate each other before any direct observation can catch them. This is the quantum vacuum, and it has been measured indirectly in countless laboratory experiments. Now combine the quantum vacuum with gravity. Add Einstein's rule that energy bends space. What do you get? You get something John Wheeler called space-time foam. Wheeler's picture is haunting. At everyday scales, space looks smooth, like the surface of a calm lake. Zoom in to the scale of an atom, and you can still treat space as flat. Zoom in further still. As you approach the Planck length, the smoothness begins to ripple. The ripples grow into waves. The waves grow into churning surf. By the time you reach the Planck scale itself, the lake has become a storm. Bubbles of geometry form and pop. Tiny temporary black holes appear and evaporate before any signal can leave them. Wormholes, brief bridges connecting one point of space to another, flicker into existence and snap shut. The entire structure of space is in violent motion. This is not a metaphor, the math demands it. The Heisenberg uncertainty principle applied to gravity says you cannot have a perfectly smooth piece of empty space. The smoother the space, the more uncertain its energy, until at the Planck scale the energy uncertainty becomes large enough to bend space into knots. You cannot photograph the foam. You cannot ever, in any conceivable experiment, see it directly. Light, as we have already learned, breaks down before it can resolve a Planck length. So the foam is permanently hidden behind the very veil of measurement. But our equations insist it is there. A second after you finish reading this sentence, an unimaginable number of tiny black holes will have appeared and vanished in the volume of your living room. Wormholes will have stitched together points half a meter apart, briefly, then disappeared. Geometries that should not exist by classical rules will have flickered into being and gone again, all without disturbing your morning coffee. The foam is too small and too brief to leave any everyday trace, but it is the substrate from which everyday space arises. Some physicists have proposed that the structure of the foam may, on rare occasions, leave fingerprints. Light traveling across vast cosmic distances might be very slightly delayed or scrambled by the foam's churn. Photons of different energies might race out of a distant gamma-ray burst and arrive at our telescopes a fraction of a second apart, the high-energy ones lagging slightly. Such effects, if real, would be the first direct evidence that the foam exists. So far, the searches have come up empty, but the equipment improves every year. Some experiments now place limits so strict that they rule out the simplest versions of the foam picture. More elaborate versions remain possible. The hunt continues. The foam, if it exists, would settle one of the oldest debates in physics. Empty space is not nothing. Empty space is the deepest something there is, a boiling, breathing, shape-shifting medium, whose smallest bubbles are the size of a Planck length, and whose lifetime is the smallest unit of time the universe permits. That smallest unit of time is a story all its own. A wormhole is a shortcut through space. Picture two distant points in the universe. a galaxy in our sky, and a galaxy on the far side of the cosmos. By normal travel, even at the speed of light, the trip would take billions of years. A wormhole would let you cross in an instant by tunneling through a hidden bridge that connects the 2 points directly. For most of the 20th century, wormholes were a mathematical curiosity. They popped out of Einstein's equations as legitimate solutions, but nobody believed they truly existed. They seemed too exotic, too convenient, too much like a science fiction plot device. Then physicists began to look at the Planck scale, and they saw wormholes everywhere. Down at the size of a Planck length, the foam churning through space does not just contain bubbles of geometry, it contains tiny tunnels, brief, fleeting microscopic shortcuts that link one Planck-sized patch to another. Some of these tunnels connect points right next to each other. Others might, in principle, connect points absurdly far apart in normal space. The tunnels open. They close. They open somewhere else. The whole pattern shifts faster than light can travel a Planck length. This is not a fringe idea. It comes from applying our most respected theories to the smallest possible scale. Quantum gravity might allow for radical alterations, such as the creation and destruction of wormholes or other topological connections. The structure of space-time at the Planck scale is not static but is constantly reconfiguring itself. Imagine a sheet of paper, smooth, flat, ordinary. Now imagine that under a very strong microscope, the paper is full of tiny holes that open and close, with threads occasionally linking one hole to another, sewing the page together in patterns invisible to the naked eye. The page still feels flat to your hand, but its real structure, at the smallest scale, is a tangle of openings and connections. Space, according to many quantum gravity theories, is just like that paper. The smoothness we see is an average over an unimaginable amount of microscopic chaos. Every cubic millimeter of empty space contains, at any given instant, a vast network of fleeting wormholes, each one Planck-sized, each one lasting less than a single Planck unit of time. If true, this raises haunting possibilities. Could information leak through these tunnels? Could two distant regions of space share a quantum connection because their underlying foam is woven through Planck-scale shortcuts? Some physicists suspect this may be the secret behind quantum entanglement, the spooky link that connects particles across any distance. The idea is sometimes summarized in a slogan, ER equals EPR. ER stands for Einstein and Rosen, who first wrote down the wormhole equations. EPR stands for Einstein, Podolsky, and Rosen, who first described entanglement. The slogan claims that every entangled pair of particles is, in some way, joined by a microscopic wormhole. The wormhole is too small and too quantum to use as a transport device, but it explains why measuring one particle instantly affects the other, no matter how far apart they are. This proposal remains controversial, but it shows the kind of thinking the Planck scale forces upon us. Geometry and information may be two faces of the same coin, and the coin is the size of a Planck length. For now, all of this is theoretical. No experiment has ever directly observed a wormhole, big or small, but the math keeps insisting they should be there at the bottom of space, opening and closing like microscopic doors. A door so small and a hallway so brief that no signal larger than a single bit could ever pass through before it slams shut. But wormholes are not the only thing flickering at the Planck scale. Time itself is. Everything we have explored so far has been about distance. The smallest distance, the smallest area, the smallest volume. But the universe has another smallest unit, and it is far stranger to picture, the smallest possible duration of time. This unit is called Planck time, and to grasp how brief it is, you have to multiply your imagination by absurdity. A Planck unit of time is roughly the time light needs to cross a Planck length. Since light is the fastest thing in nature, and the Planck length is the smallest meaningful distance, this duration becomes the shortest meaningful tick of any conceivable clock. How short is it? About 10 to the negative 44th seconds, 43 zeros after the decimal point. then a few digits, then nothing. Numbers like this rip through human intuition like wet paper. So picture this instead. The current age of the universe is about 13 billion years. Convert that to seconds. You get roughly 4 times 10 to the 17th seconds. Now compare. The number of Planck times that have ticked by since the Big Bang is roughly 10 to the 61st. A staggering count, far larger than the number of stars in every galaxy combined. Each one of those ticks was the smallest possible click of nature's clock, and each tick is so brief that during a single one of them light can cross only a Planck length. This is what physicists mean when they say the speed of light is 1 Planck length per Planck time. The two smallest units, distance and duration, are linked by the universal speed limit. They were designed to be linked. Max Planck himself, when he derived these numbers, intended them to be calibrated against the cosmos. Now consider the consequences. If time comes in smallest ticks, then nothing in nature can happen faster than 1 tick. A particle cannot move from one location to another in less than a Planck time. A measurement cannot be made faster. A thought cannot occur faster. A signal cannot propagate faster. This implies something almost philosophical. Reality, at its finest grain, is not a smooth-flowing river. It is a sequence of frames. Like a movie projected at a fixed frame rate, the universe updates 1 Planck time at a time. Between 2 consecutive frames, there is no in-between. There is no smaller slice. The next state of the cosmos is computed, displayed, and replaced by the next, all on a clock with a fixed beat. Of course, this is the radical interpretation. The cautious interpretation says that Planck time is just where our equations break, not necessarily where the universe ticks. As with the Planck length, the truth depends on the right theory of quantum gravity, which we still lack. Yet the picture of a frame-by-frame cosmos is hard to shake. Many quantum gravity proposals embrace it directly. Causal set theory, which we will meet in a few chapters, treats the universe as a sprinkling of discrete events, each separated from the next by something like a Planck time. In this view, time does not flow. Time accumulates, click by click, event by event, with no smooth motion in between. If this is the truth, then your sense of continuous experience is a kind of stitching. The brain weaves together a long string of frames into the illusion of motion. The actual reality is a flipbook, drawn on Planck scale paper, played at a rate of 10 to the 43rd pages per second. There is one more consequence, and it may be the most disturbing. If time has a smallest tick, then the very concepts of before and after lose meaning at scales below the tick. Causality itself, the chain of cause and effect that we rely on every day, may dissolve into something stranger. And that is where the next descent leads. Cause and effect, the bedrock of every scientific experiment, every legal trial, every story ever told. Strike a match. The match lights. First the strike, then the flame. Always in that order, never the reverse. This rule is so deeply built into our minds that it feels less like physics and more like common sense. Yet at the Planck scale, common sense begins to wobble. The reason is simple. Causality requires that before and after be well defined. To say A caused B, you need a clear ordering, a first, B second. Time must run as a single arrow. Events must line up like beads on a string. Now apply quantum mechanics to time itself. The uncertainty principle, which already smudges position and momentum, also smudges time and energy. To know a moment perfectly, you would need infinite uncertainty and energy. Infinite uncertainty and energy means infinite gravitational distortion, which means the smooth string of beads breaks down. At the Planck scale, the question, did A happen before B, may have no determined answer. It may have a probability of being yes and a probability of being no. The order of events themselves becomes a quantum variable. Recent experiments hint that this might be more than philosophy. Physicists in Vienna and elsewhere have built devices that put two events into what is called a quantum superposition of orders. In the lab, the events are not Planck scale, but the principle is the same. A particle can pass through gate A before gate B and through gate B before gate A simultaneously until measured. The order itself is quantum. If reality at the Planck scale behaves this way fundamentally, then the universe at the bottom is not a stage with a fixed timeline. It is a fog of possibilities, each ordering of events having some probability, none of them being the official one. The neat causal chain we experience emerges only when many Planck-scale events average out into something larger. This raises a strange question. At what scale does causality crystallize? Atoms seem to obey causality reliably, photons too. Even particles inside accelerators behave themselves, as long as the energies stay below the Planck threshold. So somewhere between the Planck scale and the atomic scale, the fuzziness of order condenses into the firm chronology we know. Nobody has worked out precisely where or how. It is one of the many unsolved problems waiting just below the surface of physics. The consequences run deep. If before and after can be quantum, then maybe the past is not as fixed as we believe. Maybe certain events at the Planck scale never quite settle into a definite history. Maybe the fabric of time at the smallest level remembers all its possibilities at once, like a book whose pages have not been numbered. Some physicists find this exhilarating, others find it terrifying. For those who like a stable cosmos with a fixed past, the Planck scale is hostile territory. There is also a tantalizing possibility for closed time loops, tiny ones, so short and so small that they could never be exploited to send signals or change the present. But they may exist constantly in the foam beneath every cubic millimeter of empty space. Microscopic loops where time bends back on itself for less than a Planck duration, then straightens out again. Causality is preserved on average. Locally, briefly, it goes haywire. None of this has been observed directly. The Planck scale remains beyond our reach. But the equations whisper that the orderly march of past, present, and future may be a kind of large-scale illusion, like the smoothness of a sand dune that hides a chaos of jiggling grains. That brings us back to a number we have already met, the speed of light. At the Planck scale, that number takes on a meaning even more profound than its everyday role. The speed of light is the most famous number in physics, about 300,000 kilometers per second, roughly 671 million miles per hour. The cosmic speed limit, the wall that no particle, no signal, no information can ever cross. Nearly every textbook treats this number as a simple fact about how fast electromagnetic waves travel. The truth runs deeper. The speed of light is the universe's exchange rate between space and time. And at the Planck scale, that exchange rate reveals itself in the simplest possible form. The connection is this: the speed of light is 1 Planck length per Planck time. Read that line carefully. The speed of light is not just a measurement, it is the rate at which the smallest unit of distance is traded for the smallest unit of time. 1 Planck length, 1 Planck tick, 1 step, 1 frame. The universe seems built so that nothing can move faster than one of its basic spatial units per one of its basic temporal units. This reframing makes the speed limit feel inevitable. Of course, nothing can outrun light. There is nothing smaller than a Planck length to step across. There is nothing briefer than a Planck time to step within. To go faster than light, you would need to skip the basic step, and the universe does not allow that. It also reveals why the speed of light shows up everywhere in physics. It links Planck units. It connects energy to mass through Einstein's famous formula. It governs how electric and magnetic fields interact. It sets the speed at which gravity propagates. All these roles are different masks of the same underlying fact. Light speed is the conversion ratio between the universe's smallest space and its smallest time. This idea has unexpected consequences. If you could somehow shrink yourself down to the Planck scale and try to move, you would discover that you can go in only a few directions per tick, forward by 1 Planck length, sideways, diagonal. In every direction, you advance 1 Planck length per tick, and no matter how hard you try, you cannot move 2 Planck lengths in 1 tick. The clock simply will not allow it. You can move slower, of course. Slower means resting some ticks while moving others. 2 ticks per step is half the speed of light. 100 ticks per step is 1/100th. 1,000,000,000,000 ticks per step is so slow you barely budge, but you can never compress 2 steps into 1 tick. Light is the line you cannot cross. Even time, in this view, becomes a sequence of light-speed exchanges. Every Planck tick, every patch of space updates itself based on signals from neighbors. Those signals travel at light speed by definition. The very flow of time emerges from light bouncing among Planck-sized cells. If this picture is right, then light is more than a phenomenon. Light is the heartbeat of the cosmos. Each beat is 1 Planck tick long. Each step the universe takes covers 1 Planck length. The familiar dance of stars and galaxies, falling apples and beating hearts, is a slow waltz overlaid on this mad cosmic strobe. There is a way, in principle, to test these ideas. If space really is built from Planck-sized cells, and light hops cell by cell, then light traveling across enormous distances might suffer tiny irregularities. A photon flashing across the cosmos for billions of years could be subtly delayed by the lumps in the road. The delay would be tiny, but across cosmic distances, tiny adds up. Astronomers have looked for exactly this effect. They picked a cosmic phenomenon famous for its violent burst of light, the gamma-ray burst. Somewhere in the distant universe, a massive star reaches the end of its life. It collapses inward in a cataclysm so violent that for a few seconds it outshines every other source in the visible cosmos combined. Light pours out across every wavelength, including the most energetic kind. Gamma rays. The flash sweeps through space at the speed of light, traveling for billions of years until it finally washes over the Earth. This is a gamma ray burst. They happen at random somewhere in the sky every day or so. Telescopes catch them. Satellites record them. And in their light, hidden among the ordinary signals, lies one of the most beautiful experiments humanity has ever performed on the structure of space itself. The idea is simple. If reality has a Planck scale graininess, then high-energy photons should feel that graininess differently from low-energy ones. The lumpiness of space should slightly slow down certain wavelengths more than others. A photon with 100 times more energy might travel a tiny fraction slower or faster than its lower energy cousin. Across a few miles, the difference would be invisible. Across billions of light years, it might add up to a measurable delay. Astronomers grabbed this lever. They started carefully timing the arrivals of gamma-ray photons from distant bursts. They measured when high-energy photons arrived at their detectors and compared that to the arrival of low-energy ones. The two should arrive at exactly the same instant if space is perfectly smooth. If space is grainy at the Planck scale, the two arrival times might differ by a tiny amount. The experiments have been running for over a decade now. The results are striking. An observational study of gamma-ray burst arrival times concluded that any putative discretization length must be substantially smaller than the Planck length to be consistent with observations. This is a remarkable finding. The universe, when probed by light traveling across cosmic distances, looks smoother than any naive Planck pixel theory predicted. If space has lumps, the lumps must be even smaller than the Planck length itself, or they must arrange themselves in a way that hides their presence from photons. Different physicists draw different conclusions from this result. Some argue that the simplest pixel theories are dead, killed by gamma-ray bursts, killed by photons that traveled from the edge of the visible universe and arrived without any sign of cosmic graininess. Others argue that more sophisticated quantum gravity theories, like loop quantum gravity, do not predict this kind of energy-dependent delay in the first place. They say the test was too simple. The real graininess is more subtle and would not show up in arrival times. Both sides agree on one thing. The experiment was a triumph. Humanity, with its fragile telescopes on a tiny rock orbiting an average star, used the explosions of dying suns billions of light-years away to test the structure of space at scales 20 orders of magnitude below an atom. The fact that we could even attempt this borders on science fiction. The hunt is not over. Newer satellites, more sensitive detectors, and longer observation times keep tightening the limits. Every year, the size of any allowed Planck scale graininess shrinks. Every year, the surviving theories become more refined. What if a delay is eventually detected? It would be one of the greatest discoveries in scientific history. The first direct experimental evidence that space at the Planck scale has structure. A door cracked open into the basement of reality. What if no delay is ever found? It would force every theorist to take seriously the most subtle and clever versions of quantum gravity, the ones that hide the foam from any classical observer. For now, gamma-ray bursts continue to flash across the sky, each one a messenger from a cosmic catastrophe billions of years old, each one carrying in its photon timing a possible whisper from the smallest scale of nature. But there is a deeper riddle. If space at the Planck scale really does have a smallest unit, then a strange question follows. Whose smallest unit is it? Different observers moving at different speeds should disagree on its size, unless someone has found a way around that problem. In 1905, Albert Einstein discovered something that broke the universe in two. He showed that distance and time depend on the observer. A moving clock ticks slower than a stationary one. A moving ruler shrinks compared to a stationary ruler. There is no single right answer for how long something is, or how long an event takes. Different observers, moving at different speeds, get different numbers. This is special relativity, and it is being tested to absurd accuracy. Particles in accelerators, atomic clocks on aircraft, GPS satellites in orbit, all confirm it. But there is a problem when you try to mix special relativity with the Planck length. If space has a smallest possible unit, and one observer measures a Planck length to be 1.6 times 10 to the negative 35th meters, then a moving observer should measure that same length to be smaller, squashed by the contraction effect. But you cannot have anything smaller than a Planck length by definition. So which observer is right? Einstein says everyone should agree on the laws of physics. Quantum gravity says the smallest length is sacred. The two requirements seem to clash. In the early 2000s, a small group of physicists proposed a fix. They called it doubly special relativity. The name comes from the fact that ordinary special relativity has one universal constant, the speed of light. Doubly special relativity has two, the speed of light and the Planck length. The idea is daring. The Planck length is treated not as a length that contracts when observers move, but as a number every observer must agree on, regardless of speed. A key feature of this approach is an observer-dependent length scale, defining the pixelation of space-time. Mathematically, this is harder than it sounds. The standard rules of relativity have to be bent. When a moving observer transforms coordinates, the usual squashing equations get modified at high energies. Below the Planck scale, the changes are invisible. At the Planck scale, the changes are crucial. They preserve the Planck length as universal. If true, this would mean every observer in the universe agrees on the smallest length. A traveler near the speed of light, a stationary observer on Earth, an alien astronomer in a distant galaxy. All would measure the Planck length to be exactly the same. It is a beautiful idea. It would explain how a smallest length can exist without breaking Einstein's symmetry. It also makes specific predictions. At extreme energies, light should travel slightly differently than at low energies. The dispersion would be tiny, but cumulative over cosmic distances, just like the gamma-ray burst tests of the previous chapter. So far, those tests have not detected the predicted effects. Either doubly special relativity is wrong, or the effect is so small it lies beyond current measurement. A different approach takes the same problem and answers it through loop quantum gravity. There, the resolution is even more subtle. In loop quantum gravity, a minimal length does not appear as a fixed structural property of space geometry. Space geometry has no fixed structural property at all in this approach. In other words, the Planck length is not a yardstick lying on the floor of the universe. It is a quantum measurement. Each observer, when they measure a length, gets a discrete answer. The smallest possible answer is the same for everyone. The framework is observer-friendly, without needing exotic relativity modifications. These are deep waters. The fight over how to reconcile the smallest length with relativity is one of the most active in theoretical physics. Both sides agree on the goal. Save Einstein. Save quantum gravity. Make them agree. The disagreement itself is illuminating. It reveals just how strange the Planck scale really is, and how difficult it is to talk about smallest things in a universe where motion is built into the rules. The struggle to make space pixelated and Einstein-friendly leads directly into one of the most counterintuitive features of relativity itself: length contraction. In 1905, when Einstein wrote down his special theory of relativity, he made one of the strangest predictions in the history of physics. Moving objects shrink. Not appear to shrink, actually shrink in the direction of their motion. A spaceship traveling at half the speed of light measures shorter, end to end, than the same spaceship at rest. A particle blasting through a tube at near light speed has a length only a fraction of its rest length. The faster the motion, the more dramatic the squashing. As an object approaches the speed of light, its length shrinks towards zero. This effect is called Lorentz contraction. It has been confirmed in countless experiments with subatomic particles. It is not an illusion, it is a real consequence of the geometry of space-time. Now apply this rule to the Planck length. If a Planck length really is the smallest possible unit of distance, then it must be the smallest for everyone, in every reference frame. But Lorentz contraction insists that lengths depend on motion. A Planck length measured by someone moving at high speed should be even shorter than a Planck length measured at rest. That is impossible by definition. The Planck length is supposed to be the floor. This contradiction is one of the deepest puzzles in modern physics. It has driven decades of theoretical struggle. An approach to quantum gravity predicting that an observer measures a minimal length must answer the question whether or not a boosted observer can observe this length, Lorentz contracted, and whether or not, in this sense, Planck scale discreteness can be compatible with some form of local Lorentz invariance. The cleverest resolution comes from loop quantum gravity. The key insight is that the Planck length in this theory is not a length in the everyday sense. It is the smallest possible outcome of a measurement. Each time an observer measures an area or volume, they get a discrete result. A boosted observer moving at high speed would still measure discrete areas, but the boost rotates the way they make the measurement. They would see different patches of space than the stationary observer would. They would measure different specific values, yet the smallest possible value, the floor of the staircase, would be the same for everyone. It is like comparing rulers in different orientations. A stationary observer holds a ruler horizontally. A moving observer holds the same ruler tilted. Each observer sees the smallest tick mark on the ruler, but each one looks at a different physical chunk of space. The tick mark itself is universal. The chunks are not. This subtle picture preserves both relativity and the smallest length. It does so by reframing the question. Length is not a property of space. Length is a measurement that observers perform. The measurement, like all quantum measurements, has a smallest possible result. That result is the same regardless of who measures. If you find this confusing, you are in good company. Some of the world's smartest physicists have spent careers on these issues. The picture has not been fully verified by experiment, but it offers a way to keep both Einstein and the Planck scale alive without bloodshed. There is another consequence worth noting. If the Planck length is a measurement floor, not a property of space, then space itself may not have a fixed smallest size. It may have only a smallest size that any specific observer can detect. This sounds mystical, but is mathematically precise. Space in this view is more like a hand of cards than a deck. The cards have specific values, but the hand, the actual reality, is determined when an observer plays. This connects to another deep idea. If space is built from measurements, and measurements take inputs and produce outputs, then space is built from computation. And the universe, at its smallest scale, may be a kind of program running itself. We have brushed against this idea before. Now it is time to take it seriously. In the 1940s, the brilliant Hungarian-American mathematician John von Neumann spent his time at the Institute for Advanced Study in Princeton, playing with a peculiar idea. He imagined a grid. On the grid, each square could be in one of two states, black or white, on or off. The squares followed a rule. Each square's next state depended on the states of its neighbors right now. He called this a cellular automaton, a simple game run on graph paper where each cell flips according to fixed local laws. What surprised von Neumann was how much complexity emerged. Starting from a few black squares on a white grid, the rules could generate intricate patterns that grew, moved, replicated, and even simulated other automata. Universal computation arose from a handful of trivial steps. The grid, given enough time, could in principle run any program ever written. Decades later, Stephen Wolfram and others took this idea and asked a wild question. What if the universe itself is a cellular automaton? What if reality at the smallest scale is a vast grid of cells, each one a Planck length on a side, each one updating its state every Planck tick according to simple local rules? Stars, galaxies, atoms, brains would all emerge as patterns in the grid, just as patterns emerge in von Neumann's toy. If true, this would be a radical reinterpretation of physics. The universe would not be made of particles or fields in the traditional sense. It would be made of bits, arranged in a Planck-scale lattice, flipping according to a deep but knowable rule. Every law of nature we have discovered, from quantum mechanics to general relativity, would be a consequence of that hidden rule, in the same way that complex weather patterns emerge from the simple thermodynamics of gas molecules. The Planck length would be the size of one cell. The Planck time would be the duration of one update. The speed of light would emerge from the constraint that no information can travel faster than one cell per tick. Quantum mechanics might arise from probabilistic update rules. Gravity might arise from the way certain patterns curve the lattice as they propagate. This is a beautiful vision. It also has serious problems. The simplest cellular automata models clash with relativity. A fixed lattice has a preferred reference frame, the frame in which the lattice is at rest. Special relativity says no such preferred frame exists. Every observer should measure the laws of physics the same way. A naive grid-based universe would let you detect motion against the grid, breaking Einstein. Modern researchers try to fix this with elaborate constructions, random graphs that look the same to all observers, probabilistic update rules that respect symmetry, multi-way systems where many possible update paths exist simultaneously. Each variation tries to preserve the spirit of cellular automata while satisfying the constraints we know reality must obey. So far, none of these models has been proven correct, but the broader idea that reality at the Planck scale is gained respect. The universe behaves in many ways like a giant computer. Information is conserved, bits add up, logical rules govern outcomes. Even quantum mechanics, with its weirdness, can be reformulated in terms of quantum computation. If reality is a computer, then we have just discovered the size of its smallest transistor, the Planck length, and the speed of its smallest clock, the Planck time, and the size of its smallest memory unit, the Planck area. From these humble Planck-scale parts, somehow the entire pageant of existence is being rendered, frame by frame, bit by bit, tile by tile. This is one face of the Planck scale. Another, equally strange, treats the universe not as a grid being updated, but as a set of disconnected events being sprinkled into being. There is a third great approach to quantum gravity, less famous than string theory or loop quantum gravity, but defended fiercely by its supporters. It is called causal set theory, and its picture of the universe at the Planck scale is the most austere of all. The picture goes like this. Forget about smooth space. Forget about lattices. Forget about continuous fields. Imagine instead a sprinkle of tiny events scattered through reality. Each event is a single point, a blink, a happening. The events have no size. They have no internal structure. They are just dots. Between any two events, there is one and only one relationship. Either one event is in the causal future of the other, meaning a signal could in principle travel from the first to the second, or it cannot. There is no other geometric data, no distance, no angle, no direction. Just causal links between events. The events are sprinkled at a density of roughly 1 per Planck 4 volume. That means, in any region of space-time, there are about as many events as there are Planck-sized boxes that fit in the region. Each event has neighbors before it and after it. The pattern of all these causal links is the causal set. This is reality according to causal set theory. Nothing else. No background, no grid, no fabric, just a discrete, sparse, sprinkled set of events with a graph of causal connections between them. Out of this graph, all of space and time emerge. The smoothness we feel in ordinary life is what you get when you stand far away from the graph. The texture of reality, like the pixels of an image, only becomes visible if you somehow zoom in to the Planck scale. Up close, you would see the bareness, the disconnection, the complete absence of anything between events. Down there, between is not a meaningful concept. This is a startling claim. It says the universe is fundamentally not continuous. There is no smooth fabric. There is no infinite divisibility. There is only a finite, discrete, growing collection of events, locked together by causal arrows. The theory has elegant features. It naturally builds in the speed of light, since causal links cannot exceed it by definition. It naturally builds in time's arrow, since the causal links have a direction. It produces, in certain limits, the smooth space-time of general relativity. It also produces a small but non-zero cosmological constant, the mysterious energy that drives the universe's accelerating expansion. This was actually predicted before observers found it. Critics complain that causal set theory has trouble producing the rich variety of particles and forces we see. A skeleton of causal links does not obviously give rise to electrons and photons. Defenders counter that this is the wrong question to ask of a foundational theory. Particles, in this view, are patterns in the causal set, not separate entities. Whether or not causal set theory is right, it shows the kind of imagination required at the Planck scale. The continuous picture of space is so deeply baked into our minds that we struggle to imagine alternatives. Yet the math demands alternatives. Once you accept that smooth space breaks down at the Planck length, you have to invent new pictures to take its place. Sprinkles of events, loops of geometry, vibrating strings, self-updating grids. Each picture is an attempt to describe a reality nobody has ever seen. All of these pictures share one obvious feature. They are far below the reach of any current experiment. Which raises a sobering question. If we cannot even come close to probing the Planck scale, what hope do we have of ever testing these theories? The answer involves the most powerful machines humanity has ever built, and a brutal reality check on their limits. The Large Hadron Collider sits beneath the border of France and Switzerland. It is a ring 27 kilometers around, equipped with magnets cooled to colder than outer space. Inside, beams of protons whip around the ring at nearly the speed of light, then collide head-on. The collisions release energies higher than anything else humans have ever produced. The wreckage of those collisions is studied by detectors as large as office buildings. This machine is the crown jewel of human science. It cost over $10 billion. It took decades to build. It involves the labor of tens of thousands of scientists and engineers from across the world. It found the Higgs boson. It tests the standard model of particle physics with breathtaking precision. And yet, when it comes to probing the Planck scale, the Large Hadron Collider is a joke. The collider can resolve distances down to about 10 to the negative 19th meters. The Planck length is 10 to the negative 35th meters. The gap between them is 16 orders of magnitude. To reach the Planck scale, you would need a machine 10,000 trillion times more powerful than the one we have. This is not a small upgrade. This is not a few % improvement. This is a leap by a factor that exceeds the number of stars in our galaxy. To imagine it, picture making the Large Hadron Collider longer to compensate. The current ring is 27 kilometers. To reach Planck-scale energies with a similar accelerator design, you would need a ring whose circumference is roughly the size of our entire galaxy, 100,000 light-years across. There is no engineering trick to shrink that. The amount of energy needed to probe a Planck length is fixed by the laws of physics. To pack that energy into a small enough volume, you need an accelerator of cosmic proportions. Some physicists have run the numbers and concluded that a Planck-scale accelerator is, for practical purposes, impossible. Even if humanity expanded across our entire galaxy and turned every available star into raw fuel, we would still not have the resources to build such a machine. The Planck scale, by direct collision, is forever beyond our reach. This is a crushing realization. It means the foam, the loops, the strings, the cellular grids may never be observed by colliding particles in a tube. The most natural experimental approach, the one that has driven progress in physics for the last 100 years, runs out of road 16 orders of magnitude short of the goal. But human cleverness has its own answers. If you cannot reach the Planck scale by force, you can reach it by patience. Some theories predict that the foam, even if astronomically small, leaves cumulative traces in light traveling vast distances. Photons crossing the universe for billions of years pass through unimaginable numbers of Planck-scale fluctuations. If even a tiny effect builds up per crossing, the cumulative result might be detectable. We have already seen the gamma-ray burst tests 2 chapters back. Other approaches use atomic clocks of staggering precision, or quantum interferometers tuned to detect the smallest possible vibrations, or the cosmic microwave background, the leftover light from the Big Bang itself, frozen onto the sky like ancient ice. Each of these approaches is a side door to the Planck scale, not a direct entry. A sneaky route. They probe the Planck length through its faint shadows, not through brute force. But there is one wild idea that takes the brute force route and refuses to give up. It involves a detector so vast that it dwarfs anything ever proposed. A detector whose size is measured not in meters or kilometers, but in astronomical units. In the early 2025s, a group of physicists at Caltech began asking a brutally honest question. If reaching the Planck scale by collision is impossible, what would it take to detect quantum gravity by other means? They started running calculations. The numbers came back nightmarish, but possible. A leading idea is to use a gravitational wave detector. Earth already has several. The Laser Interferometer Gravitational Wave Observatory, called LIGO, has 2 arms, each 4 kilometers long. Inside each arm, lasers bounce between mirrors. When a gravitational wave passes through, it stretches and squeezes the arms by less than the width of a proton. The detector is sensitive enough to catch this microscopic stretching. It has detected the collision of black holes billions of light years away. But LIGO is not nearly sensitive enough to feel the foam at the Planck scale. To do that, you would need a much, much larger detector. One way to go is to make something the size of the solar system and look for signatures of quantum gravity that way. Read that line and pause. A detector the size of the solar system. Spacecraft scattered across hundreds of millions of miles, bouncing laser signals between them, watching for vibrations so faint that they would correspond to the stirring of Planck scale fluctuations. The arms of the detector would not be kilometers, but astronomical units. The same kind of distance that separates the Sun from Saturn. This is not pure fantasy. The European Space Agency, in partnership with NASA, has been planning a smaller version called LISA, the Laser Interferometer Space Antenna. It will fly 3 spacecraft in formation, separated by a few million kilometers in heliocentric orbit. LISA is planned for launch in the coming decade. It will detect gravitational waves of much lower frequency than LIGO can hear. It will see the mergers of supermassive black holes and the early universe's gravitational rumble. But LISA is a baby compared to what you would need to chase the Planck foam. You would need an array spanning the entire inner solar system, spacecraft as far apart as the orbit of Mars from the orbit of Mercury, possibly farther. The technology to keep them in such precise formation does not yet exist, but the equations say it could work. With enough patience and enough laser stability, such a detector could feel the slight murmurs of quantum gravity rippling across the cosmos. Other proposals are even wilder. Some physicists have suggested using the entire galaxy as a detector. Pulsars, which are rapidly spinning neutron stars, beam radio signals across vast distances with clock-like regularity. By timing the arrivals of these signals from different pulsars in different directions, astronomers can reconstruct gravitational waves with wavelengths of light years. This pulsar timing array technique has already detected the long wavelength hum of the universe. With enough refinement, it might catch the highest frequency gravitational ripples that bear the imprint of Planck scale physics. There is no guarantee any of these methods will work. The Planck scale is so far below current measurements that we may need entirely new approaches we have not yet imagined. But the willingness of physicists to even propose detectors the size of the solar system, or arrays that span the galaxy, shows the determination to pry open this last great mystery. The Planck scale might be hidden behind walls of energy and walls of distance, but humanity has a habit of climbing impossible walls. Slowly, expensively, brilliantly, we keep finding side paths to the things we want to know. And there is a fascinating chapter of cosmic history where the Planck scale was not hidden at all, a moment when the entire universe, every star and galaxy and atom that would ever exist, was packed into a single Planck volume. Roll the clock backward. Watch the galaxies drift toward each other instead of apart. Watch them merge, smaller and smaller, denser and denser. Run the cosmos in reverse for 13 billion years. What do you find at the bottom of the rewind? You find a moment when the entire observable universe, every atom that would ever form, every planet, every star, every black hole, every photon now traveling the cosmos, was packed into a region the size of a single Planck length. This is the Planck epoch, the first sliver of time in the universe's history. It lasted for 1 Planck unit of time, about 10 to the negative 44th seconds. Before that moment, our equations cannot describe what was happening because we do not have a working theory of quantum gravity. After that moment, the universe became describable, just barely, by extreme physics. During the Planck epoch, the temperature was unimaginable, the density was unimaginable. All 4 forces of nature, the gravity that holds galaxies, the electromagnetism that lights your screen, and the 2 nuclear forces that bind atoms, were merged into a single unified force. There were no particles in the modern sense. There were no atoms. There was no space the way we know it. There was only a churning, foaming quantum gravitational soup, packed into a volume so small it could fit billions of times inside a single proton. This is one of the most extreme regimes ever proposed in physics. And it is no fantasy. It is a direct consequence of running our best equations backward as far as they will go. What happened during the Planck epoch is the deepest unsolved problem in cosmology. Without a theory of quantum gravity, we cannot say the math we have produces nonsense, infinite densities, infinite curvatures, time and space melting into each other, The universe, at its first moment, sits in a region where our two great theories cancel each other out, leaving us blind. Yet certain features can be guessed. The Planck epoch was probably governed by quantum gravitational effects on every scale, because at that moment, every scale was the Planck scale. The entire universe was one Planck-sized fluctuation. The same physics that today produces tiny wormholes and brief black holes inside empty space was, during the Planck epoch, producing the cosmos itself. In a sense, our universe began as a single Planck-scale event, and it grew. As the Planck epoch ended and time advanced, the universe expanded, cooled, and decoupled into the four separate forces we now know. Particles condensed out of the soup, atoms formed, stars eventually ignited, galaxies took shape, all from that initial Planck-sized seed. This raises strange questions. If the cosmos began as a Planck volume, what was outside it? Probably nothing, since outside means a notion of space that may not have applied yet. What came before the Planck epoch? Probably no answer is meaningful, since time itself may not have existed yet. The Planck scale may be where time itself begins. Some theorists go further. They suggest that the Planck epoch was not the absolute beginning. It might have been the boundary between our universe and a previous one, a bounce, a collision, a pinch in a larger structure. Various models, including loop quantum cosmology, predict that the Big Bang was actually a transition, a Planck-scale handover from a contracting cosmos to an expanding one. These ideas remain unproven, but they show how the Planck scale ties the smallest length to the largest event in cosmic history. The same number that limits how closely we can measure space also marks the moment when space itself began. And the imprint of the Planck epoch is not just history, it is etched onto the sky, a trillionth of a trillionth of a trillionth of a second. After the Big Bang, the universe did something insane. In a span of time so short that no human word can capture it, the cosmos expanded by a factor of at least 10 to the 26th. Distances that had been smaller than a proton ballooned into regions larger than the planet Earth. The expansion happened faster than light, but no rule was broken, because it was space itself that stretched, not anything moving through space. This is cosmic inflation, the leading theory for what happened in the first instance of the universe. Inflation does not begin at the absolute beginning. It begins after the Planck epoch, when the universe is already a tiny fraction of a second old. But the signature of inflation, the reason it explains so many features of our cosmos, lies in what it did to Planck-scale fluctuations. Before inflation, the universe was tiny. Quantum mechanics demanded that empty space at the smallest scales boil with fluctuations. Foam, wormholes, vacuum jitters, all churning at the Planck scale, exactly as we have described in earlier chapters. These fluctuations were normally too small to matter. They averaged out. They never grew. Then inflation kicked in. The space in which the fluctuations lived expanded by a colossal factor. What had been a Planck-scale ripple suddenly became a galaxy-scale ripple. Tiny quantum fuzz stretched across the cosmos became giant patches of slightly higher and slightly lower density. Those patches did not vanish. They froze into the early universe, like ripples on the surface of a pond, suddenly turned to ice. As the cosmos continued to evolve, the higher density patches pulled in matter through gravity. Galaxies began to form preferentially in those regions. Clusters of galaxies grew on the largest patches. Voids opened up between them. The vast cosmic web visible today was sewn by quantum fluctuations of size, smaller than a Planck length, blown up to cosmic scales by inflation. This is one of the most extraordinary claims in modern cosmology. Every galaxy you see, every star, every solar system, every planet, including Earth itself, exists in its current location because of a quantum jitter that occurred at the Planck scale in the first sliver of cosmic time. There is direct evidence for this. The cosmic microwave background, the leftover radiation from the early universe, has tiny temperature variations across the sky. fluctuations of 1 part in 100,000. These variations have a specific statistical pattern. The pattern matches what inflation predicts when Planck scale fluctuations are stretched by inflation. The match is precise. It is one of the most stunning successes of modern cosmology. In other words, we can see the imprint of the Planck scale on the sky. We just cannot see the Planck scale directly. The early universe acted as a microscope. It magnified the foam. The foam, magnified, became galaxies. We are the descendants of Planck scale ripples. This connects the smallest scale in physics to the largest. The Planck length, normally hidden beneath 16 orders of magnitude of energy, gave birth to every visible structure in the cosmos. Without those fluctuations, the universe would have been smooth and featureless. No matter would ever have clumped. No stars would ever have formed. No galaxies would ever have spun. No planets would ever have cooled enough for chemistry. No life would ever have appeared. The Planck length, in this sense, is not just a curiosity. It is the seed of everything you have ever seen. And just as the Planck scale created everything, it may also be where everything slowly returns. There is one more cosmic process whispering at the Planck scale, and it ties the universe's largest objects to its smallest fluctuations. In 1974, a young Stephen Hawking did something that shocked his colleagues. He showed, with cold mathematics, that black holes are not perfectly black. They glow, they emit a faint radiation. They lose mass over time, they evaporate. This was a stunning prediction, and it traced its origins directly to Planck scale physics. Empty space, even far from any matter, is not truly empty. Quantum fluctuations constantly produce pairs of virtual particles. A particle and its antiparticle pop into existence, exist for a fraction of a second, then annihilate each other. The dance happens everywhere, all the time. It is the same boiling vacuum we have been describing in earlier chapters. Now place a black hole nearby. The vacuum still boils. Pairs of virtual particles still pop up. But near the event horizon of the black hole, something different can happen. One member of the pair might fall into the black hole. The other might escape. Instead of annihilating, the pair gets separated. The escaped particle becomes real. It carries energy. It flies away. To balance the books, the black hole loses an equivalent amount of mass. Multiplied across the entire surface of the event horizon, this process produces a slow but steady stream of escaping particles. The black hole shines, faintly with its own light. The radiation has a temperature. The temperature is inversely proportional to the black hole's mass. A small black hole is hot. A big black hole is cold. For a black hole the mass of the Sun, the Hawking temperature is so cold that the radiation is impossible to detect, far below the temperature of empty space. The black hole would lose mass over a span of time, so long it makes the current age of the universe look like a single tick. For a black hole the mass of a mountain, the Hawking temperature is hotter and the evaporation faster. Such black holes might have formed in the early universe and might still be evaporating now. For a black hole near the Planck mass, the Hawking temperature is unimaginable, hotter than anything in the universe. The evaporation is explosive. The black hole shrinks toward the Planck length itself, and here is where the math gives up. When a black hole reaches the Planck size, our equations stop being trustworthy. The same blend of quantum mechanics and gravity that breaks at the Planck length makes it impossible to predict the final moment of evaporation. Some theories say the black hole completely vanishes in a final burst. Others say a Planck-sized remnant survives forever, a tiny stable lump containing a finite memory of everything that fell into the original black hole. Yet others say the information escapes in subtle correlations within the radiation itself, recovered only by an observer who collects every photon emitted. Whichever turns out to be correct, the evaporation process ties the largest objects in the universe, supermassive black holes, to the smallest fluctuations in nature, the Planck scale boil of empty space. Black holes leak because of the foam leaks because of quantum gravity. Quantum gravity is governed by the Planck scale. Hawking's discovery showed that black holes have a temperature, an entropy, and a finite lifetime. All three properties are calculated using a constant called the Planck length squared. The Planck scale is in the recipe. It is the salt in every formula. It also raises the deepest unsolved problem in modern theoretical physics. Where does the information go when a black hole evaporates? Did everything that fell in get destroyed? Was it preserved? Was it scrambled? The answer, whatever it turns out to be, is hiding at the Planck scale. The Planck length, again, is the address of the answer. But there is one more story before we reach the bottom. A story that takes everything we have learned and asks an almost forbidden question. If reality is pixelated, if it is a code, if it computes itself one Planck step at a time, then who or what made the source code? And could the entire universe be a computation running on hardware somewhere outside it? In 2003, the philosopher Nick Bostrom published a paper that made many scientists uncomfortable. The paper argued that, given certain assumptions about the future of computing, it is statistically more likely that we live in a computer simulation than in a base reality. The argument runs like this. Suppose civilizations far more advanced than ours can build computers powerful enough to simulate entire universes, including conscious beings inside them. Suppose those civilizations choose to run many such simulations. Then, statistically, the number of simulated minds far exceeds the number of base reality minds. Therefore, any mind reasoning about its own existence, like yours right now, is far more likely to be a simulated mind than a base reality one. Most physicists do not take this argument as a serious empirical claim, but the rise of pixel-based pictures of reality has given the argument unexpected ammunition. If the universe truly does have a smallest unit of distance and a smallest unit of time, then it shares a deep similarity with computer simulations. Both have a finite resolution. Both proceed in discrete steps. Both work with bits of information. Some thinkers have asked whether the Planck length might be evidence of a simulation. After all, every game has a finite resolution. Every render has a smallest pixel. Every simulation has a step size. If our universe shows a hard flaw at one specific size, maybe that flaw is the resolution chosen by whoever programmed the cosmos. The argument is provocative. It is also speculative. There are perfectly good reasons, having nothing to do with simulations, why the Planck length might exist. We have spent the last 20 chapters exploring those reasons. Quantum gravity demands a smallest scale. Information theory demands 1 bit per Planck area. Black holes seal off any attempt to look smaller. The Planck length emerges from the constants of nature themselves, without invoking any external programmer. Still, the simulation idea cannot be definitively ruled out. There is no experiment that distinguishes a Planck pixelated universe that is fundamental from one that is simulated. Both look the same from the inside. A simulated being, examining the laws of physics from within, would discover the same Planck scale at the bottom. It would have no way to tell the difference. This raises philosophical questions that no equation can answer. If the universe is simulated, what is the underlying reality of the simulators like? Is it also pixelated? Does it also have a smallest scale? Do simulations exist in an infinite regress, with universes inside universes inside universes, each one running its own version of the Planck length? Some physicists find these questions exciting. Others find them tiresome. They argue that the simulation idea is unfalsifiable, and therefore not really a scientific question. It cannot be tested. It cannot be disproved. It floats outside the realm of physics, in the domain of philosophy and theology. There is one reasonable way to engage the question scientifically. Look for cracks in the simulation, glitches, inconsistencies, features of reality that look like rounding errors or computational shortcuts. Some researchers have proposed specific tests. Look for anisotropy in the cosmic microwave background that could indicate a finite simulation grid. Look for tiny violations of relativity at the Planck scale that might betray a numerical algorithm. Look for repeated numerical patterns in the constants of nature that hint at a designer's preferences. So far, no such cracks have been found. The cosmos seems consistent at every scale we can measure. The Planck length, if it really is a simulation pixel, is doing an excellent job of looking like a fundamental feature of nature. Whether or not we are simulated, the conversation forces us to confront the strangeness of the Planck scale. It is small enough to mark the bottom of our equations. It is granular enough to resemble a pixel. It is informational enough to encode bits. Combine these properties, and the question of simulation becomes hard to ignore, even for the most hard-headed skeptic. But there is one final question that lies even deeper than the simulation puzzle. It is the question that has driven this entire journey. What, if anything, exists below the Planck length? We have reached the bottom of the journey. 32 chapters of foam, loops, strings, holograms, bits, simulations, and ancient cosmic ripples. Each chapter in its own way has been a different lens on the same haunting question. What happens at the smallest scale of nature? The honest answer, the one no theoretical physicist will avoid in private, is this: we do not know. The Planck length is the deepest unsolved riddle in science. Below it, all our equations break. Below it, no measurement can ever reach. Below it, even the categories of physics, position and time, cause and effect, length and duration, lose their meaning. The Planck length is not just a small distance. It is a horizon, a fundamental limit on what physics, as we currently practice it, can describe. Some physicists believe that if a complete theory of quantum gravity is ever found, it will reveal the Planck length to be a genuine smallest unit, a real pixel of reality, the bottom of the staircase. In that case, asking what exists below the Planck length will be like asking what is north of the North Pole. The question itself will be malformed. There simply will be no smaller distance. Other physicists believe the Planck length is an artifact of our ignorance. They suspect that future theories will reveal substructure even below the Planck scale, new layers, new surprises, new scales of organization that we cannot yet imagine. In that case, the journey downward will continue, with new chapters yet to be written. There is no consensus. Some of the deepest minds of our age, the ones who have spent careers grappling with these questions, disagree. Loop quantum gravity says the Planck length is a real flaw. String theory says strings are roughly the Planck size, but that further structure may exist within the math. Causal set theory says the discreteness of events is fundamental. Cellular automata models say a Planck scale grid underlies all of physics. Doubly special relativity says the Planck length is observer independent. Each picture is mathematically beautiful. None has been verified. What unites all these pictures is a single, eerie fact. They all agree that something extraordinary happens at the Planck scale. They all agree that our familiar concepts must give way to something stranger. They all agree that the universe, at its smallest, is not the smooth, eternal, continuous backdrop our intuitions imagine. Reality, at the bottom, is granular, or at least it behaves as if it is. This is one of the most profound discoveries in the history of human thought. For most of our species' history, we assumed space was infinitely divisible. We assumed time was a smooth river. We assumed the universe could be cut, in principle, as small as you wished. We were wrong. There is a wall. The wall is sharp. The wall is at the Planck length. What exists beyond that wall, if the word beyond even applies, may be something so unlike everyday reality that human minds cannot picture it. Some theorists describe it as a chaotic foam, others as a network of disconnected events, others as an information substrate, others as the source code of a simulation, others as a quantum vacuum so deeply different from classical space that all our spatial words fail. The truth, when it is finally discovered, may surprise everyone. It may combine elements of all these pictures, or it may be something nobody has yet imagined, a framework so strange it will require entirely new mathematics, new concepts, new ways of thinking about reality. Whatever it turns out to be, The Planck length will remain the threshold, the doorway, the address where the everyday cosmos ends and the deepest mysteries begin. Every breath you take, every thought in your head, every star burning in the night sky, every photon traveling across the cosmos ultimately rests on whatever happens at this scale. We cannot see it, we cannot measure it, but it is there. The universe holds one final secret behind a wall of pure gravity, and the wall is the size of a Planck length. Standing at the edge, looking down into a region forever sealed from view, the only honest response is awe. The cosmos hides its smallest truth from us, and in hiding it, the cosmos reminds us of the most important lesson in physics. The deeper you look, the stranger reality becomes, and there is always a deeper layer waiting,